So welcome to today's session on sequence and series. And for today's session, I'm sorry, wait, for some reason I kept on losing my mouse every time I use my tablet. Should be connected. You fixed that for a while. Oh, there you go. Should be fixed now. Okay, so we're gonna talk about sequences and series. And we're gonna start with the basics, which is number sequence. So number sequence is an ordered list of numbers defined by rules. And if you must have learned before that there are two kinds of number sequences, which is the arithmetic sequence and the geometric sequence. So there are several ways to describe these sequences. For example, if you have a sequence of 4, 5, 6, 7, or etc. Doing this is a form of describing a sequence. This is what you call as listing a sequence. Well, wording a sequence would be describing it. For example, in this sequence, you can say that, the sequence starts at 4 and increases by 1 each time. That's how you describe it. And then for formulas, it's how you usually write down something like Tn equals to 3 plus n. 3 plus n. This would be the formula of this sequence would be in something like this form, which I will explain further later. And you can also graph your sequence, which is something I think you would rarely do. Like first sequence, second, third, fourth. Example like this. 4, 8, then 4, 5, 6, 7. Close enough. Let's just say it's an estimation of the graph. But in this graph, you don't pull a line because you're supposed to depict the sequences, not form an equation out of it. And okay, so usually in sequences, we have this thing called the n term or the like general term. It's usually written in the n or in IB. I think it's written in UN. And what this basically says is like what you call the n term. So for example, if you have for this sequence, you have T3 or U3, then that would be 7. And if we insert it through this formula, you can also find the same result. So for example, T3 equals to 3 plus 3. So you see this and this should be the same if you have like the same number, close to 6. And in this case, it is 6. All right, so I'm gonna go into arithmetic sequences. Arithmetic sequences are usually the sequences that have the same constant difference, or it's added with the same constant. Like for example, if we have something like 3, 5, 7, 9, you can see that its sequence formula is constantly added by 2. And you can usually try to look for its formula by doing UN equals to the first sequence plus n minus 1 b. if we insert this, that would be 3 plus n minus 1, and d would be 2, because this is a common difference to n. And you can pretty much keep it this way, or you can also just expand this if you want. 3 plus 2n minus 2, so that would be 1 plus 2n. And this is both the same thing, but like for the sake of if you for the sake of convenience and uniformity, you can just use this one and refer to this one, because it's easier for you to remember the formula. And for a second, it's kind of like an expression of saying like it's not that hard to remember. So like, for example, if you have u1, you kind of, it's kind of like saying that you discard this part, and then so you can have 3, and then for u2, it's kind of like saying 3 plus 2 minus 1. So you can get like this becomes 1, right? 1 times 2. So you can have plus 2, and then to continue, you're gonna have like 2 times 2, which is like plus 2 plus 2. So it's more, I suppose it's like more easier to take in by mathematical terms. And then for so in arithmetic sequences, you sometimes use them to approximate things. And this is more for like, I think this is more for AI. So basically, I don't really have an example. Let me look for one for a sec. Well, I can't seem to find one, so screw that. Okay, let's just skip that for later, because I don't want to waste a lot of time looking for that. So next up we have geometric sequence. Geometric sequence, unlike arithmetic sequence, is denoted by un equals to u1 times r n minus 1. So if arithmetic sequence is the addition subtraction version, this is usually the multiplication division version. That's how you usually that's how I usually view it. So this is kind of like the same thing as the arithmetic sequence. So the formula itself wants you to like remove the first ratio, so you can have u1 and then multiply it for the rest of it. An example of this would be something like 2, 4, 8, 16. So if you have this kind of sequence, and then you want to look for the This is called ratio, by the way. And this is the first term. If you want to look for example, okay, so in this case, you would obviously want to find the ratio first. And to find the ratio, you divide this by this, this by this, and this by this. And you can see that this is, the ratio of it is 2. So, and the first term is also 2. So it's 2 times 2, n minus 1, to the power of n minus 1, equals to un. And then if you insert this, this n, you can find that, for example, if you have u4, that would be 2 times 2 to the power of 2 minus 1, 4 minus 1, equals to 2 times 2 to the power of 3, so that would be 2 to the power of 4, and that results in 16, or this one. 1, 2, 3, 4. Okay, so in geometric sequence, there's an interesting property that you can see. And this happens when you have three consecutive terms next to each other. Let's just say this is A and B and C. So if you have this, B over A can equal to C over B because of the nature of its ratio. This is for example, if this is multiplied by 3, and then this is also multiplied by 3, that's kind of like that's kind of the same as 3A over A equals to 3B over B in some way. So we can move this and turn it into B squared equals to CA, and that would get you square root of plus minus CA equals to B. In this case, because it's a regular sequence, we can kind of assume that square root of CA is positive. But I don't think I should explain further about like why it is, because you're not really talking about algebra. Yeah, I see something in the chat, so oh. Geometric mean. Okay, so something related to geometric sequences would be growth and decay. This is again, I think more into AI-ish in terms of like the applications and stuff. So what's going on here seems similar to the geometric sequence, right? You see that the UO is actually pretty similar to UI. It just means like this one means initial. This one means first sequence. I mean, if you think about it, it's like the same thing, but just different interpretations, because one has to be like real life applications, and then the other one is just a sequence term. But the difference with both of these is that one has n minus 1 and one has n. And that's because usually if you count this growth, they're asking you, for example, if you have like 1 year, and then you have, let's just say we have like penguin population growth. So in the first year, in the start of the first year, we have 200 as their population. And then they want to ask in the end of the year, how much did they increase if they have a 6% growth? So since they ask in the end of the year, they expect the growth to already happen. And thus we can just skip the first term because the first term is already existing. They just want like the next sequence in the end. I'm not sure if I phrased that correctly, but I hope you guys can understand what I'm talking about. Yeah, I just removed this. All right. Okay, so let's just say, let me just give you an example to I guess give a further understanding of this thing. Okay, let's say that again we have the population of penguins. Their initial population is 200, and then they have they experience a 6% growth from 2000 until 2005. So if I ask, how long does it take for them to reach twice its population? Take to reach twice. So in this case, you're trying to find the UN as twice of its initial population. That would be 2 times 200, right? Which is 400. And wait, let me just rewrite this down so you can remember. Rn. And then the ratio of it is 6%. That would be, the ratio would be 1.06 because it said they experienced 6% growth. Oops, 6% growth, which is if you turn 6% into decimals, it would turn into 0.06. But then the reason why I added a 1 is because the penguins, the population of penguins have a 0.6% growth, and if you want to only see the growth itself, like how much it increased, you would multiply this number, the initial, to the growth, 0.06. But you want to see like its total growth, so you want to see the population staying as 200 plus an extra of the ratio of the growth. So ratio result. So you're supposed to, this should be 1 or 100% plus 6%. That would be 106% or 1.06. And since it asks for how long does it take to reach twice its population, the power, the n, is trying to ask you the how long, the duration of it. So that would be 400 equals to 200 times 1.06 to the power of n. And we're supposed to look for n. For this, you can pretty much insert this in your calculator. You can compute it through GDC using like the formula of this. And I can't really specifically explain to you how, because there are a lot of different GDC calculators. So again, like I said in my previous sessions, it's the best if you can look for GDC and then the topic name, subject name, and then your calculator name in Google, and then YouTube videos would appear in or Google Google Guides would appear. Not really Google Guides, I'm so sorry, but more like some guides would appear through the Google search engine, and that would help you a lot. Unless if you want to actually read your calculator manual one by one, which I doubt many people do. But if you want to do it manually, you can just do it algebraically, which is by doing this. This becomes 2. And then compute this as a logarithm. I haven't explained about this, but I think it will be explained in like future sessions, because the book hasn't really explained about because I'm just doing this based on a book. But basically, this is the base, and this is the exponent, and this is the answer. And basically, in logarithm, you turn this part into the base, and this one to like the answer of it. And using logarithm, you can search for the powers of it, and that results in 11.89 or around 11.9. Okay, so since I've covered about growth and decay, now I'm gonna cover about financial mathematics. Financial mathematics actually also have like a lot of correlations with geometric sequence and growth and decay, because if you see the format of the formulas, they're quite similar. Times 1 plus I to the power of n. This is interest. This is the duration. Commonly, it's usually in form of year, but there are also exceptions where they use months or weeks. But the common ones would be year. And this is the initial money or the initial interest. Okay, but then if you look at the AA or AI syllabus, they give you this formula. FV equals to PV times 1 plus R, 100K to the power of Kn. And this means this refers to the final compound result, the final compound money, compound interest rate, whatever. And then this is also referring to the initial compound rate or interest. I don't remember the specific term of it, but the point is they have the same they have similarities. And then here's where it gets different. So the R in the book's version refers to ratio and percentage. So you can see that like what they're trying to do is to make it that you you don't need to convert the percentage ratio to decimals. But then there's K. So you might ask like, why does this K exist? This K is mostly used when they expect like when they expect annual compound interest, but then at the same time the compound interest is multiplied per term. So examples of this would be something like quarter ones, or for example, if you have monthly compound interest, but they expect you to find the results yearly. So, and I have an example right here that we can work on to demonstrate like how it works. So in this case, okay, so you can see that in this example, the money is compounded yearly, but they expect it's compounded like quarterly or monthly, but they expect like yearly interest rate or yearly results. And this is kind of like why we need to have to use this formula. And how you do it is, in this case, we don't really have a specific amount. So let's just assume the PV is 1000. And then, okay, so let's just insert it in the formula 1000 plus, oh, sorry, times 1 plus R. R is 6% over 100 times K. So the first question asks for quarterly, and that's where you insert the K. The K becomes 4 since they demand like quarter compounds, but then they also expect yearly interest rates, which I mean I think it's weird, but it's just financial things, you know. Okay, and let's just assume that they expect it by, oh wait, hold up. Let's just assume they expect it by like 2 years or so. So the money you would get from this would be this. Would be 1126.492, and that's around 1030 in 3 significant figures. And then if it's done monthly, that would be 1000 times 1 plus 6% over 100 divided by 12 to the power of 12 times 2. And that results in 127.159, around the same result as this in 3 significant figures, that is. But then let's just compare it to yearly compounds. 1 plus 6 over 100 to the power of 2. And that results in 1123.6, or around 1,120 in 3 significant figures. So you can see the difference between yearly compounds and the monthly compounds. They may be a bit complicated, but then they have higher results if the compounding is more frequently done. This is quarterly, monthly, yearly. Okay. Oh yeah, by the way, before we move on to the next topic, this formula can also be applied in the GDC. So if you have a GDC, there's this section where they allow you, they have finance formulas like the simple interest, the compound interest, and etc. etc. So if you have no idea what's going on and you're lazy, you can always just insert it into your GDC to make things easier. And okay, so inflation and depreciation, they're pretty similar. The difference is just inflation is adding up stuff, but then depreciation is minus decreasing stuff. So for example, if we have this formula, or this formula to make things easier, IN. So for depreciation, obviously the interest becomes positive, but then for depreciation, the interest becomes negative. You can kind of logic that out, I suppose. Okay, so now we are going into series. Series is basically a sum of the sequences we've learned. And there are 2 kinds of series, which is the finite series and the infinite series. The finite series is the type where you usually, if you haven't known, usually you have a formula, and then you try to look for the sum of the series until a certain point. So that's why it's Sn. But for infinite series, usually you try to calculate its total series from 1 to infinity. And I'll explain about how this exists later, because I mean, in the first place, it sounds trippy to have an infinite series, but they do exist. Okay, so something that we're gonna have to learn would be the sigma notation. So I presume the syllabus won't expect you to cover this before learning IB, before going into the course. So this symbol looks, for someone that hasn't experienced it before, at least for me, in my experience, the symbol would look like very complicated and very weird and very like trippy. But it's actually simpler than you think. So, for example, if you have a sequence of 2, 3, 4, 5, 6. For example, we have the sequence, and then you want to find the sum of these sequences: 1, 2, 3, 4, 5. That would be as 5. And if we try to like look for the formula of the sequence, that would be around 2 plus n. So you want to find the sum of these sequences. The long way of doing it would be to add 2 plus 3 plus 4 plus 5 plus 6. And if we have a lot of sequences, a long chain of them, this would be very tedious to do, or very tedious to write in general. So how we shorten that is we use the sigma notation in a way so that we don't have to write something like this. So we draw the E notation, and then the n would be the 5. That is like the final limit, or the last term that you want to add. And then the k, the k can be changed into n, which means that n equals 1. So it starts with like 1. It starts with adding 1, and then you can write. Oh wait, sorry. This is supposed to be 1 plus n, not n plus 1. No, it's supposed to be 1 plus n, not 2 plus n. Sorry. And then you can just write 1 plus n. So this is going to mean 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4 plus 1 plus 5. So it's actually less, so if you're new to this notation, it's actually less intimidating than you think. It's actually very helpful. And it's very helpful, especially if you're using calculators, because you can just literally insert the numbers in here, and then you can get the results from a calculator. But for like general writing, it's just like, okay, so yeah, so it's an like I said before, it's an effective way to write like sums of sequences. Okay, so this sigma has some interesting properties. Like the first property that they have is AK plus BK, sum of numbers in AK plus BK, where K is 1 until n. So when you have this, you can turn it into K equals 1, AK plus n sigma K equals 1 BK. Oh, very nice. I actually forgot how or why this happens. Okay, so the reason why this happens is because let's just say we have something. Oh, okay, so the reason why this happens is because it's kind of like saying, okay, for example, if we have the sequence of, hold up, no, that's different. No, that's supposed to, okay. Um, yeah, I completely forgot why this happens, but I know why this one happens. So, assuming that C is a constant is basically like number that has the same value every time in like in this situation, then this is possible because it's kind of like saying, for example, we have 3, k equals to 1, and then we have c, for example, let's just say c is 5, 5 a k, then that would mean 5 times 1 plus 5 times 2 plus 5 times 3. But then if you move the constant out into this, that's also the equivalent of saying 5 times 1 plus 2 plus 3. It's just like a way of factoring the 5 out of the equation, you see? So like if you multiply this way, then you will get the same result as this. And you should get the same result. So that would be 5 plus 10 plus 15. And that's 30. This is also 30. 5 times 1 plus 2 plus 3, that's 6 plus 30. For this one, if you have a constant, and then like something like this, then the result would be c times n. And the reason why it's like this is because let's just say we have something like 3, k equal 1, and then the constant is again 5. That's like saying, it's kind of like saying 5 plus 5 plus 5, because from 1 till 3, you cannot really insert the k, right, into this formula or equation. So you're just literally just inputting 5 and 5 and 5. And since there are, from 1 till 3, there's 3 times of it, then you can easily say that it's 5 times 3. And up till now, I still can't remember why this is like this. So
I'm guessing it's because k changes, right? And you're basically, the change happens inside the bracket, and it would just be the same if you separate it out as two different sigma notation. Does that make sense?
Yeah, that does. At least for me, because like visually I get it, but then by like words, I don't know how to explain it.
Like, let's say an example, a equals 3 and b equals 2, right?
Let's say something like um k equal 1. Like let's just say it's something like this again. That would that would be 1 plus It's like saying 1 plus 2 plus 3 plus 1 plus 2 plus 3. I think it's something like that.
Yeah.
Yeah. So you can
And
kind of separate it.
right. And the other one is like 1 plus 1 plus like 2 plus 2. That would be this one, right? And this one would be the same as that one.
Yeah.
Does that make sense? Yeah.
Then for so we have formulas for arithmetic series, finite geometric series. And instead of explaining like the concept behind it, I'm just gonna explain why the formula is like this. So you can for AA people, you can understand like how to prove it, but then for AI, you can at least understand how the formula came to be, and I guess be more confident in applying it in some way because you understand the concept. So okay. Oh, I'm so sorry. I didn't see your chat. I just opened it just now. Okay, so you see in arithmetic series, if you want to find the sum of a series, that's kind of like saying u1 plus u2 plus u3 plus u4 plus u5 until un. And that's also the equivalent of saying something like u1 plus u1 plus d plus u1 plus 2d and etc. until un. And so we can also flip this, right? We can also flip it in a way so that it's un plus un plus like etc. 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 Just say like un minus d plus etc. until u1. So if we want to add all of these up, it becomes 2Sn, and that would equal to u1 plus un plus u1 plus un until un plus u1 I mean like u1 plus un n times. So since this is like the same thing from crossing this out, you can turn this into a more condensed version, which is 2Sn equals to n times u1 plus un. And to find the formula, you can just move this so it becomes n over 2 plus u1 plus un. And that's how you find this formula. But then for the formula underneath this, it's from substituting the un as u1 plus n minus 1 times d. So if you substitute this, it becomes n over 2 times u1 plus u1 plus n minus 9 times d. And that would be n over 2 times 2u1 plus n minus 1 times d. So, well, you don't have to remember the formula since it's in the formula book, but I guess that's something you can know, so you don't feel like what kind of formula is this and where do you derive it from, you know, kind of feeling. Okay, so for the finite geometric series, you can also find it from manipulating the algebra. As you may know, the nature of the Sn for the geometric series would be something like A times AR times AR square times, plus AR plus AR square plus blah 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 until AR to the power n minus 1. So a way to manipulate it so we can find the formula of this would be to multiply Sn by minus r. So by multiplying Sn into minus r, you turn A into minus AR, and then you turn this into minus AR squared, and you keep on going until you turn this into minus ARN. So if you add this all up, all together, Sn minus R times Sn, you're gonna have a lot of values that you can cross out. Wait, let's just say like minus AR n minus 1, so ARN, and you only be left with A minus AR to the power of n. Oh yeah, forgot to say that A is like the first, it's the same thing as like the first value, the first term of it. So we can factor out the Sn, right, into Sn times 1 minus R. And we can also factor out the A into A parentheses A minus Rn. And then you move the terms so there's only Sn in one side. Minus R to the power of n over 1 minus R. And that's how you get the formulas of these. Assuming that R is not equal to 1. Because if R is equal to 1, then you can't find the result. Okay, so last part we have infinite geometric sequence. Infinite geometric sequences are special because basically what happens in geometric sequences is that if you have a ratio that is more than 1, for example, like 1.5 or 2 or 3 or whatever, any value bigger than 1, then the results, your answers are going to slowly increase or maybe even exponentially increase. For example, like if the first term is 1 and we have the ratio as 2, then that would be 1, 2, 4, 8, 16, and then etc. etc. So if you add up like an infinite amount of it infinitely, then obviously the answer would be infinity, or because you can't count it, because it's just like constantly increasing. There's no way that you can find the infinite sum of it. However, there are also ratios that are less than 1. That would be something like the kind of ratios with fractions, like 1 over 2, 1 over 4, or 0 point something something. So what happens is that it slowly converges into a certain amount. For example, we have the first term as 1 again, and then we have the ratio as 0 0.5. Then you'd have 1, 0 0.5, 0 0.25, and then 0 0.125. And it slowly goes into a very small amount, so we can sort of calculate the total sum of the infinite geometric sequence. And you do that by doing the first term over 1 minus r. And personally, I haven't figured out why or Googled on why that's the case, so I can't really explain to you right now about it. So that's pretty much it for today's session. We can work on some questions if you like. And thank you for coming.